Yes. Shall we start? So in second session, little harder problem, and I'll focus more on different number theoretic techniques. For example, one such technique is, or in many problems we use Sophie-German identity. That's your common technique. Or formula for quadratic. Or Fermat's descent method. And I'm not taking that I was not knowing you are already little familiar with number theory, but otherwise a nice technique or concept is number theory congruence, which looks something like this: A congruent B, and your modulus of suitable number like say 3, 4, 5, 10, whatever. That's another technique. So there are many such standard techniques in number theory which are used for Olympiad problems. So I will test some of them. Obviously, I'm not doing congruence because at first everyone may not be doing congruence. Yeah. So we'll do one problem from the first problem set, and that is following: find two positive integers. Find two positive integers a and b such that a plus b is equal to a. Yeah, so this has some geometric interpretation. In fact, Babylonians worked with problems on rectangles where perimeter equal to something. Okay. So for example, suppose I have a rectangle with sides inside y, and say for example, say perimeter is the perimeter is 20 and area is equal to say 20. So this led them to quadratic equation. So what is perimeter? Is times x plus y, right? So x plus y is 10 and xy is 24. Now luckily this is an integer solution, but otherwise how to work such problem? So the idea is following: I can replace y or x from first equation into other, and I get quadratic. So x into 10 minus x is equal to 20, and you get a quadratic. So that's how they studied quadratic with the problem that's perimeter equal to some number times area. So this problem is something similar to that. Semi-perimeter equals area. How many such rectangles are there? Let's try to work. So point is, in fact, if area are real numbers, there will be many solutions to this. In fact, infinitely many solutions. But we are working with integers. That's the advantage. and positive integers. So one way is following. Then I say b is equal to ab minus a, which is a times something, right? So b is a times something, right? And what it means in terms of number theory? Shall I say this means a divides b, which shortly we show as a vertical line b. This does not mean a by b or b by a. It means this number divides this number. That's it. Okay. So a divides b. If this notation clear with you, we'll be using quite often. So a divides b. Fine. So which means b is a times some integer. Now similarly, it's very much symmetric, right? So can I say similarly a divides b? Similarly, b divides a divides b, and b divides c, right? Can I say that by symmetry? Or how will you simplify if I want to claim b divides b?
Will take minus
A is equal to AB minus B.
Yeah. So a equal to ab minus b, and you take b constant, right? Or many times this is standard technique or standard principle which you can use. Like look at symmetry. If I interchange a and b, if I replace this by b, if I replace this by a, this by b, this by a, you see our equation is again same, right? And which means if I am getting result a divides b, similarly I am getting b divides c. Is that fine? So what can we conclude from this? One number divides other divides b.
both are equal.
Plus minus B.
Yeah, and they are positive. So basically, shall I say a equal to b? More generally, I can say a equal to plus minus b. But now I know they are both positive. So it can't be a equal to minus b, right? So shall I say a equal to b? Now once I get a equal to b, I can put it here. So a plus a is equal to a square. I am putting b as a, right? So 2a is a square. What are the roots? Either a is 0, but I know numbers are positive, so it can't be 0. And that means I can cancel out a, right? And I get a equal to. So if a is 2, b is also 2. Yeah. So that's the only solution, which means the only rectangle whose semi-perimeter equals area is basically square with side 2. So if sides are 2, 2, the perimeter turns out to be 8. Semi-perimeter turns out to be 4. Area turns out to be 4. So semi-perimeter equals area. That's geometric understanding of the problem. Okay. Go ahead. Now problems are little tougher, so I try to go a little slower at the first lecture. Yeah, so that's one technique. Okay. Now let's see another technique. In fact, in all India's problem can be done with many ways. And here is one such example. So you can do it in 2-3 different ways. Another standard way is following: AB minus A minus B equal to 0. Right? And I'll add 1. In fact, I'll add suitable number so that it gets factored. So AB minus A minus B plus 1. In fact, by practice, you understand what number to be added so that it gets factors. This is equal to 1. Right? And what are the factors of this side now?
A minus 1.
Yeah, good. A minus 1 into B minus 1 is equal to 1. Okay? But I know these are positive, right? And their product is 1. What's the only case? They are integers.
A is equal to B.
Positive integers. Implies A minus 1 must be 1. B minus 1 must be 1. That's the only way I get product as 1. Okay? Suppose instead of 1, there would have been 4. I get different cases, like this is 4, this is 1, or this is 2, this is 2, or this is 1, this is 4. right? But in this case, it's only 1. So only case where product of two integers is 1. So note that we are focusing on the part that they are integers. So I get a minus 1 is 1, b minus 1 is 1, which again if you like a is to b is 2. That is the solution. Right? Another nice way, which is again connected to geometry, is following. Yeah. So what I do is, they are positive, I know they are not 0. I divide by AB. So A plus B upon AB is equal to 1. Right? So what can I say? A upon AB plus B upon AB is equal to 1. Right? So which means 1 by B plus 1 by A, and rearrange 1 by A plus 1 by B is equal to 1. And in case of integers, if I get reciprocals equal to something, again I can focus on the bounds of A and B. That's another technique in number theory. Now I'll talk in terms of different techniques, standard number theory techniques. The bounds on A and B. Okay, so for example, they are positive. Can I have, suppose let's assume, whose either they are equal or one number is bigger than the other. Right? Yeah. So suppose A is greater than or equal to B. Can I do that? Yes. So suppose this is smaller, this is larger, or perhaps they may be equal. And then 1 by B, right, is less than 1 by A. We agree with that? Static reciprocals. The bigger number gives smaller reciprocal. And this is wrong. 1 by A is smaller than 1 by B, right? Yeah, this is that. Now suppose my B is greater than, assume that my B is greater than, shall I say 1 by B will be less than half? 1 by B is less than half, right? Yeah. So in that case, this plus this will be less than half plus half. 1 by A plus 1 by B, that is less than, this is less than half. 1 by B is also less than half. So it's less than 1. It can't be equal to 1. Right? So if my B is greater than 2, there is no solution. Okay? Yeah. So which means my B can be either 1 or 2. Right? Right from this side. So this implies B has to be less than or 2. Again, if B is 1, if B is 1, I get something wrong. 1 by A plus 1 is 1. Which means 1 by A is 0. Is there anything wrong in that? 1 by A is 0. Cross multiply. I get 1 equal to 0. Okay. So this is again not possible. Or something which is wrong in terms of Feynman that's called as, so you must have come across many times this word contradiction. I get some contradiction. Okay. Something which is wrong, totally wrong. So B can't be 1. So B can't be 1. Right? If B is 2, if B is 2, I put value B. Value of B. 1 by A plus 1 by 2 is 1. So 1 by A is 1 minus half. This is half of it. So it means A is 2. So again I get A is to B. So we are solved in 3 different ways. A is to B is 2. Is that okay? In fact, such fractions are called as unit fractions. 1 by A type fractions are called as unit fractions. And there is a lot of history. when Egyptians they used to write every fraction in terms of unit fractions. So let's say for example, suppose say there are 5 pizzas in a party and there are 8 students, 8 for that party. So how should we divide it? Everyone should get equal part. So everyone should get 5/8. We have to divide among 8 students equally. So first of all, divide these into 2 equal parts. So how many parts are these? 8 parts. So give one piece to each of them. So that means each will get 1/2 or 1/2, 1/2, 1/2. Right? And this they divide to 8 equal parts. Okay. So everyone should get 1/2 plus 1/8. Which means in other words 5/8 must be equal to 1/2 plus 1/2. So they used to write every fraction in terms of unit fraction because that's something easy to handle with. Right? Yeah. There is one more interesting activity related to this property. Let's see. Do you have protractors? Can you measure angle? Then we'll do some activity, small activity, a quick activity. Yeah. Okay. So draw a straight line. Draw a straight line. All of you can measure the angles. We have protractors. So draw a line with angle 16 to the first line. So let's say this is horizontal line with angle 16. Can I help? Intro will be down as well. Yeah, so draw one line, draw another line, and fix it. Look at it. Everyone has protractor, or you can tell each other. Yeah, draw one more line to fix it. So this angle and this angle is 60. So total angle is 120. Right. Get there with each other. Okay. Everyone is clear what we are doing? Yes. Okay, so for example, yes, so look here. For example, 1/2 plus 1/2 is 1/1, right? Okay. Or say 1/6 plus 1/3 is 1/2. Okay. So this is better. This is better. You can measure 6 centimeters on one line. You can measure 3 centimeters on third line. Third line. Keep the same scale. Whatever you are choosing here, keep the same scale here. And now simply join this and this by straight line. Okay. Here you will get answer. This is exactly check. This is where you will get answer. Maybe somewhere ideas are not. If you fill in proper this should be true. This leg should be true. Okay, so what is more general result and say the general result? You draw 3 lines with 66 degree. If this distance is A, if this distance is B, if we join these two, this distance is C, then 1 by A plus 1 by B is equal to 1 by C. That is one of the problems. Check the second sheet. Okay, you haven't got second sheet. Madam, this is second sheet. Yeah, you get it. Okay, so that's another problem. One by A plus 1 by B equal to 1 by C. Okay, so this we have to prove. Geometry में कौन अच्छा है? Yeah. So we'll prove this. If we make 3 lines with angle 60-60, if this distance is A, this is B, by join them, this has to be and this is C, then 1 by A plus 1 by B is 1 by C. Okay? Yeah. So we have to prove this. Let me just check back. Geometry. Okay. How do we do that? I'm number 3. I don't do geometry. आपको हेल्प करना पड़ेगा. Yeah, this is A, this is B, this is C. What I have to prove is to prove that 1 by A plus 1 by B is 1 by C. आपने geometry किया है ना 2 दिन? Yeah, बोलो. So like for example, this is also same as A plus B upon AB equal to 1 by C. Right? So I'll take one of them on other side. So like A plus B upon B is A by C. I have to prove something like this. And where do we get such ratios? किधर आते हैं geometry में?
So length of angle bisector is 2AB upon A plus B cos 60.
No, something like this ratios. Where do we get it? case of geometry?
Sine rule.
Something upon something is equal to something upon something.
Sine rule.
Sine rule or little easier than that. Yeah, so something like in similar triangles, right? Suppose I have two similar triangles. Then I get ratios like a is to b is same as x is to y, right? Is that okay? So somewhere I need to find some similar triangles, right? So we need to do some construction. Okay. Now, for example, I'll extend this on back side. Yeah, then how much is this angle? All of that this is again 60 because angle in a straight line is 180, right? So this is again 60. Now what I do is this side is B and mark this side here. I take this distance to be B so that I get this total length is A plus B. A plus B, right? Yes. I'll join these two and I get another triangle. Right? Now I want how much is this angle and how much is this angle. Why? Why?
Because isosceles triangle.
Yeah. So this side is B and this side is B. So at least to begin with, we can say it is isosceles triangle, right? So two sides are same, which means these two angles must be same. Okay. So if this is x, this is also x, and together I will get x plus 60 equal to 180. That gives me 2x is 120. That gives me x is 60. So now I know this angle is 60, this angle is 60, which means it is not isosceles, it is actually equilateral triangle. Okay. Yeah. But anyway, so this angle is 60, this side will be bigger. Okay, this is B, this is B. It is equilateral triangle, all sides must be same. So this also must be B. Okay. Now some similarity or combination, whatever. So try to get A plus B upon B equal to A by C. You tell me the proof. I'm number 3, I don't do geometry. If you want, I'll name these points and you tell me some similarity. The A, B, this point is C, this is D, E. Now what things are similar which will give us something like this? Yeah, somebody? Now this we want to get, right? But from this angle, which are similar. So triangle ADC is similar to triangle AEB. Everyone agrees? I don't know geometry. All the agree with this?
Yes, sir.
Yeah. So now ADC is similar to AEB. Now corresponding sides, like for example, in AEB I get A plus B is to B is same as this side is to this side. So that is A is to C. Do you get that? And once I get this, cross multiply. So I hope some of you are 9, 10 students and you must have done some resistances in parallel and so on, right? Yeah. So what is that formula? 1 by R1 plus 1 by R2 is equal to 1 by R6, right? Equivalent resistance. And if you want to find this as well, you can directly find the resistance, right? So this one has simplified A upon AB, 1 by B, B upon AB, 1 by B. Okay, so look at that example of 1 by 6 plus 1 by 3 equal to 1 by 3. Now 6, 3 and 2 together, what is the GCD common factor? जो तीनों में common आएगा ऐसा क्या common factor है? What is क्या common factor between 6, 3 and 2? तीनों में 6, 3 and 2. Yes. So this is 1, right? Now whenever A, B, C are 1, then GCD of A, B, C is 1 and 1 by A plus 1 by B equal to 1 by C. What one can prove is, or what one can show is, A plus B is square as well as A minus C is a square as well as B minus C is a square. So for example, 6 plus 3, 9 is a square, 6 minus 2, 4 is a square, and 3 minus 2, 1 is a square. So we have to prove that problem. Number क्या बोलते हैं? Second sheet, 7th problem. Second sheet, 7th problem. Let ABC be positive integers with no common factor such that 1 by A plus 1 by B equal to 1 by C. Prove that A plus B, A minus C, B minus C are perfect squares. There is no common factor between A, B, C. Prove that A plus B is square. First let's show A plus B is square and then immediately we get A minus C, B minus C are also square. Yes, so first of all, do you agree that A must be clearly A must be greater than C? Right? Because 1 by A plus something is 1 by C. Right? So 1 by A must be smaller than 1 by C. Cross multiplying C should be less than A. Right? Right? Or if you are looking, this is little theoretical. Look at it. Yeah, so if 1 by A plus 1 by B is 1 by C, A will be greater than C, and similarly B will be greater than C. Okay. Now, let me put let A equal to, because it is bigger than C, I will put it C plus something, some number. Okay, and similarly B equal to C plus something. Yeah, so now you work with अभी इसके आगे आप करो थोड़ा सिंपलीफाई सो 1 by c plus n plus 1 by c plus n equal to 1 by c. How do we add fractions? 1 by plus 1 by 2. How do we add? It's a plus b upon a, right? Addition of these two. Yeah, so what do I get? I cross multiply. So c into all of this. Is 2c plus m plus n is equal to 1 into this. So in Olympiads, we should have some patience with calculation. Many times calculations are tedious. And should be patiently doing that thing. Yes, what is implies? C into 2c square plus cm plus cn is equal to c square plus cn plus cn plus mn. Right? Right? So now some cancellations and we will get c square equal to mn. Right? C square equal to mn. Right? Again, this is standard number theory technique. If at all, GCD of two numbers is 1, that is their co-prime, and their product is square, then individually this is square as well as this is square. Okay. Life m is square as well as n is square. And there is nothing special about square. More generally, if this is cube, m is cube, n is cube. Right? If this is 4 power, m is 4 power, n is 4 power. Right? So one can prove that. I am not going into those details. One can prove. One can prove instead of mn is 1. And product is c square. So implies m is c square. And m is some square. And n is also some square. Right? So what can I say about relation between c and x and y? Mn is x square y square. So c square is x square y square. So c is xy, right? C is xy. Yeah. Now what is equal to a plus b square, right? So what is a plus b? A plus b is c plus c plus n plus n. Then I say 2c plus n plus n. And what is c? C is xy. What is n? N is x square. What is n? N is y square. Okay? So what do we get? A plus b is x plus y square. So we have our first part a plus b square, and as well as a minus c and b minus c are m and n, but they are already square. Right? So also a minus c is n, which is y square, and b minus c is n, which is x square. Then, in fact, this problem occurred in RMO 1992 and somewhat similar based on same idea occurred 1 year earlier in MOOP. So we have solved one MO and RMO question. Okay. Yeah. Problems based on Sophie-Lerman technique. Yeah. Sophie-Lerman was a French mathematician. So the surname is German. He was a French mathematician from 8th century. She was a French mathematician. She proved first case of Fermat's last theorem. Fermat's last theorem. Okay. All of you know what is Fermat's last theorem? So, Verma again conjectured that x raised to n plus y raised to n equal to z raised to n has no solution in natural numbers. For n greater than or equal to 3. For example, if you replace this by 2, then there are so many solutions, infinitely many solutions, right? And just if you replace by anything bigger than 2, there is no solution. So that result was unproved for 300 years. Finally, in 1993-94, Andrew Weiss for the first time claimed that he has solved the pair. But expert found one small gap in that group, small mistake, small gap in that group, which he has to settle down. And after 1 year of efforts in 1994-95, along with his student Taylor, he settled that gap. He proved the pair. Right? What are mistake? He corrected that mistake. And there is a Fields medal, like Nobel in maths, the biggest medal is Fields medal. So which is given to mathematicians who are below 40 years and who have done something great in maths. So by the time when he claimed it for the first time, he was 40 years. But by the time he settled it, he was 41 years old and he could not get Fields medal. So he was given some special silver disc. Instead of Fields medal, he was given some silver disc for his work in number theory in mathematics. And in fact, later on, many of his students, like for example, I hope you have heard of this word, this name Manjul Bhargava. Manjul Bhargava was, he is Andrew Weiss student. He received a Fields medal later in 2014, I think. Yes, so that's the story about Fermat's last theorem. So, Sophie-Lerman claimed one case of Fermat's last theorem. Okay, in fact, unfortunately, in those days, even in French universities, girls were not admitted or they were not allowed to take lessons in university. And she learned under a nickname, Mr. Lamla. So She posed as if like she was born and with name Ravana, and she took lectures in university and later lectures again. So later on, she worked also in Shri on electricity. And her work on electricity received a medal which was used in building Eiffel Tower. Okay. And if you look at Eiffel Tower, there is a metal strip which contains names of mathematicians and scientists whose theory has been used. But because she was a girl, her name is not there. So that was the unfortunate case. Yes, so that's the story of Sophie German. So she had done a lot of big work, and as compared to that maths, whatever we are doing, it's a very small result, not that great. But still, it has got the name of Sophie German. Okay, so let me give the problem. 4 raised to 545. I think problem number 6 or something. Plus 545 raised to 4. Show that this is competent. And we'll do a little more general result. So what I do is, I want to focus on that Sophie German technique. So more generally, 4 raised to n plus n raised to 4 for n greater than 1 is composite. What happens if n is 1? N is 1, what will happen? That will be 5, which is prime, which is not composite. So let's see. Clearly, if n is even, this number is even greater than 2. Right? Is even and greater than 2. So composite. So it's composite, right? So that's one case, simple case, and even. Okay. So we have to deal with odd case and odd. And very simple, but it's interesting, very interesting. If n is odd, 4 raised to n plus n raised to 4, I can write as 2 raised to 2 raised to n plus n square square. Can I write this as 2 raised to n square plus n square square? Right?
Sir, I can.
Yes, I will.
Sir, you have to do sir 4 times 4 power 544 plus 545 power 4. Then we can apply 8 power 4 plus 3 power 4 and just transform.
Yeah, that is okay, but let's first finish this one. And we just put n equal to 545. That is composite, right? Yeah. So, how should we proceed further? Or I mean, what is something else technique? So, you try to complete the square. Suppose I have a square and b square, how should I complete square?
Yes, AB minus 2AB.
Yeah, add 2ab, subtract 2ab, and this completes the square, right? I do the same thing then. 2 raised to n square plus n square square plus 2 times 2 raised to n into n square, right? Minus 2 times 2 raised to n into n square. Okay. So do I get whole square? 2 raised to n plus n square the whole square, right? Minus 2 raised to n plus 1 law of matrices times n square. Okay, But just in the morning you would talk about which numbers are squares. So now I know n is odd and plus 1 is even. So can I say this is square? Right? So let me put a little more precisely. N is odd as n plus 1 is even. Say n plus 1 equal to 2k. So I put this as 2k. And which means that I say this is 2 raised to k n the whole square. Correct? 2 raised to k into n the whole square. All of you agree with that? Now what is this? This is a square minus b square form. And how do you factorize that? A square minus b square. A plus b to a minus b. So I get two factors, right? I get two factors. So it's composite, right? So this is 2 raised to n plus n square minus 2 raised to k n into 2 raised to n plus n square plus 2 raised to k n. Okay, so I get two factors and you can see or prove easily that both are greater than 1. So it is composite. Okay. Now take the fact that for n equal to 1, this is 2 plus 1 minus this term will turn out to be 2. N is 1, k is 1. So 2 plus 1 minus 2, and therefore this term turns out to be 1 into something. In fact, 1 into 5. Right? So it turns out to be prime, not composite. Okay? But otherwise, for n greater than 1, this is greater than 1, this is greater than 1. So n raised to 4 plus 4 raised to n is composite. Is composite for n greater than 1. Okay? Is that right? Yeah. And now in our case, just put n equal to 545. So we are done. Okay? Or if you want, we take the same steps by replacing n by 545. And that's okay. So we'll do the first one. Very simple. Right? Find all 6-digit numbers x1, x2, x3, x4, x5, x6 made using digits 1, 2, 3, 4, 5, 6 each exactly once such that 1 divides x1. So I have some 6-digit number. First digit is x1, second digit is x2, third is x3, x4, x5, x6 using digits 1, 2, 3, 4, 5, 6 exactly once. So for example, my number may be 1, 2, 3, 4, 5, 6, or it may be 6, 5, 4, 3, 2, 1, anything. Okay? Such that just if I look at first number x1, 1 divides that. In fact, every number is divided by 1. 1 divides every number. 2 divides 12. 2 divides number made up of first two numbers. X first two digits. Then we should divide x1, x2, x3, a 3-digit number. 4 divides x1, x2, x3, x4. 5 divides x1, x2, x3, x4, x5, and 6 divided the total number. Is the problem clear? Yes, so this is something simple everyone can do. You can keep answering me. So like, what should be last digit? What should be last digit? In terms of parity, even odd. So as some number which is 6 digited, some number which is 6 digited, this part is divisible by 2, right? So shall I say x2 must be even, right? This part must be divisible by 4, so x4 must be even, and the whole number also divisible by 6, so that should be even. All of you agree? So 3 even digits out of 1, 2, 3, 4, 5, 6. They stand here. Second place, fourth place, sixth place. Okay. Right. Where will be 5? Where will be 5? X5 must be 5. All of you agree? Because 5 divides x1 into x3 is 4 x5. So one digit is fixed. Right? X5. All of you agree? X5 must be 5. Okay. And these three are even. Okay. So now how many odds are left? One. Only two. 1 and 3. So 1 and 3 must be either it should be 1 even, 3 even, 5 even, or 3 even, 1 even, 5 even. So there must be only these two types, right? Now, this whole number should be divisible by 3. So what can I say about number here, digit here? What is the test of divisibility? The sum of digits should be divisible by 3. Right? So this sum is 1 plus 3, 4, 4 plus e. I mean, whatever that even number. It should be multiple of 3. So for example, I can put 2 here, right? Any other choice? Even number which will give me sum of digits which is multiple of 3. Any other choice? 4 or 6? If I put 6 here, will it work? So only one choice, 2, right? Same is the case here. Right? Now here I should put either 4 or 6 such that this number is divisible by 4. What is the test of divisibility by 4? Yes, the last 2 digits should be divisible by 4. So what should I put here? 4 or 6? 6. What should I put here? 4 or 6? And I have no choice left. 4 has to be here. Okay. So there are exactly 2 numbers spread above 1, 2, 3, 4, 5, 6 such that 1 divides x1, 2 divides x1, x2, 3 divides x1, x2, x3, 4 divides x1, x2, x3, x4, 5 divides x1, x2, x3, x4, x5, 6 divides the whole number. Right? Now, you can check all conditions are satisfied by both these numbers. Yeah, one more interesting question that was again from some RMO. Second problem. next to this one. 100 students are standing for a parade, maybe say NCC or PT whatever. So initially they are all standing, right? Their NCC teacher commands all of them to sit down. So first command is sit down, all of you, right? So जो खड़े लोग थे सब लोग बैठ गए. Then next command, second command. Every second student should change the position. Change the position means those who are sitting should stand, those who are standing should sit, right? But already all are sitting. Now every second person should stand, right? All are sitting. So every second person should change the position. So sitting while standing, right? So after second command, what's the position? Initially, 1, 2, 3, 4, up to 100. All are standing. All are standing. I don't know how to draw sitting position. So now, yeah. So second command. All are sitting now. All are sitting. After the third command, every second person should change. No, sorry, this is first one. This is first one.
Sir,
Yes.
every student, so can I tell us? Sir, can I tell you?
Okay. So after first command, everybody is sitting. Right? Then after second command, every second person should be standing. So first is sitting, second is standing, third is sitting, fourth is standing, and so on. What about 100? 100 will change the pose. Why? 100 will be standing. Why? So you see, second, fourth, sixth, eighth, all are changing to standing position. Right? So 100 is even, and which means 100 also should change the position. Then what is third command? Every third position and every third person should change the position. So this is first person is sitting, second team will be sitting, no. Second is standing. Every third person. So third person was sitting, he stands. Fourth, no change. Five, no change. Six, we change the position. Six was standing, six will be sitting. Right? Six will be sitting, and so on. So like this, there are 100 commands. So in fourth order, every fourth person changes the position. In fifth, every fifth person changes the position, and so on. In last command, only the last person, 100% will change the position. Is the order clear? Question clear? So by the end of 100 commands, who will be sitting and who will be standing?
Squares are standing.
Yeah. So what happens in fact? How the student change positions?
Based on their factors.
Depends on what are the factors. Like for example, student number say 12. Student number 12 will change position at what command?
Second.
First command. Because in first command everyone changes the position. Right? Second, third. Because 12 is multiple of 2, it's multiple of 3. So when I say every second person, 12 will change. Every third person, so 12 will again change. Every fourth person, 12 will change the position. Every fifth person, so 5th, 10th, 15th and so on. So 12 won't change position. Right? What about 6? Every 6 person, so 6, 12, 18, 24 and so on. So 12 will change position. Next, at 7 command, 8 command, 9, 10, 11, he won't change position. lastly at 12, and after 12 you won't change the position, right? Because numbers will be larger than that. All of you agree? So how many times 12 changes position? As many times as its number of divisors, right? How many number of divisors are there? 1, 2, 3, 4, 5, 6. So it should say student number n changes position at k order where k divides n, right? And say for example, if I change position 2 times, standing will be sitting, sitting will be standing again, right? If I change position 4 times, standing will be sitting, standing, sitting, standing. So if I change even number of times, I will be standing, right? Those who change position even number of times will stand, and those who change position for odd number of times will sit down. All of you agree? Yeah. Right? Yeah. So, what should I say? If number of divisors is even person or the student is standing position, is in standing position, and if number of divisors is odd, will be sitting position. So ultimately question is which numbers have even number of divisors and which numbers have odd number of divisors, right? Okay. Yeah. So which numbers have odd divisors and which numbers have even divisors? Okay, that's the question. So for example, let's take say 6 has 1. In fact, I'm writing this way. 6 is 1 into 6, 2 into 3, and so it has 4 divisors. That is even. Okay. 8 is 1 into 8, 2 into 4. So there are 4 divisors. Right? What is 9? 9 is 1 into 9, 3 into 3. 3 into 3. Which means I don't get another factor, I get 3 itself, right? So this is odd. And what about 10? 1 into 10, 2 into 5. So there are 4 divisors. So you see, in fact, if my number is a square, perfect square, then square root will have no other pair, no other number to pair with, right? And therefore it will have odd number of factors. Okay. So for example, say 16 is 1 into 16, 2 into 8, 4 into 4, and this is one and the same, right? I counted only once. So it has even plus 1, odd number of factors. Okay, agree with that? So shall I say squares have odd number of factors and non-squares have even number of factors? Okay, because for square there is one number which is square with itself, so there is no separate divisor. Okay. So I count 2 plus 2, 4 plus 1, 5. Right? So I get odd number of divisors. So let's say squares have odd number of divisors and non-squares, because for non-squares I can pair, right? Have even number of divisors. Yes, once again look at the argument. Given any number n, anything, say 10, 20, 30, whatever, right? At what order it changes the position? At number k or at k order, where k is divisor of n. Okay. Yes. So let's look at once again. So student number n changes position at k order if k divides n. How much take with that? Okay. Then if number of, so which means it changes position how many times? As many as number of divisors. Right? Okay. So if number of divisors is even, person will be standing at the end. And if number of divisors is odd, person will be sitting at the end. Is that okay? Now, which numbers are having odd divisors? Which numbers have even divisors? Squares have odd number of divisors, and non-squares have even number of divisors. Okay. So, which persons or which students will be sitting? 1, 4, 9, 16, 25, and so on. 36, 49, 64, 81, and 100 will be sitting. Others will be standing. Okay, agree with the argument? Okay. So we go ahead. Yeah, one more technique where we use formula for quadratic. What do you know? Okay, determine all integers and for which n square plus 19n plus 92 is a perfect square. Yes, the idea is following. Suppose you can write down with me because there is some calculation involved. Suppose n square plus 19n plus 92 is some square, right? Is equal to say, what can I say? N square. Right? And now you treat this as quadratic in n, treating m as constant. Treat this as a quadratic in n. So what is formula? Suppose that ax square plus bx plus c equal to 0. What are the roots of x square plus bx plus c? What is formula for root?
Minus b plus
Minus b.
e plus 5.
Follow me again. That's the formula. Right? Now, suppose inside this, if I get a perfect square, then I get some integer answer. Okay. Otherwise, if this is not a perfect square, then it will be irrational number. Okay. Yeah. So in this case, it implies n is minus 90 plus minus root of b square 19 square minus 4 times AC. A is 1, A is 1, C is 92 minus 10. Okay? Upon 2, A is 1. Yeah. So shall I say this is integer, this is integer, and that means quantity inside the square root should be perfect square. Okay, agree? Because if that is not a perfect square, this number will be irrational, and therefore n will be irrational. Whereas what we have is n is natural number, integer. Okay? So since n is integer, it implies 19 square minus 4 times 92 minus n square should be some perfect square. Super good. Yes. So simplify this. 19 square is 361 minus 8 368 plus 2x square is x square. So minus 7 plus 4x square. Please check the sign whether I have done calculations correctly.
Sir.
Yeah. So what should we do further? Yeah. So take one term to other side. So when I take minus 7 to that side, it will become plus 4x square minus x square is 7. And again, what is this? A plus b, a minus b. 4 plus x, 2 minus x is equal to 7.
1 7 or 7.
Yeah, so either I get this is 7, this is 1, or this is 1, this is 7, right? Of course, if you want integers, you allow negative numbers also. So I tell all possible cases. So this is 7, and this is 1, or this is 1, this is 7, or this is minus 7, this is minus 1, or this is minus 1, this is minus 7. So you have to deal with 4 cases. Now how shall I solve this? There is plus minus x, I simply add them. So adding I get 4n equal to 8, which means m is 2. But once my m is 2, I put it here, and I get x equal to 3. Yes, so what will be n in that case? N is minus 19 plus minus root of this quantity we have called as x square. Right? So n is minus 19 plus x. What will take it? By 20. Yeah. So x is 3. Minus it. Okay. So you can find similarly other case. This is 1, this is 7. And check what you get. It's a quadratic. There will be two solutions. Let me the second one. So that will give me another value of 10. The second value of n is minus 11. Okay. And you can actually put it here and check in this one. N equal to minus 8 and n equal to minus 11. And in fact, both of them give you same square 4. Okay. Yeah, so that's one common technique, use of quadratic formula. Right? And what's the advantage? Because this side is integer, this must be perfect square. That's the technique. Okay, we'll do the last one. That's IMO question. And which means after we solve that, we have solved every question. Junior IMO, IOQ, PRMO, IMO, IMO, and now IMO. Okay. Then D is something different than 2, 5, 13. So what you have to show is okay, we'll try to understand the problem first. Okay, wording is difficult because it's IMO question. Now you take, we don't know what is D, and you take any two numbers, two different numbers, take 2 into 5, product 2 into 5 minus 1, and you see that is square, right? Then 2 into 13 minus 1, that is also square. 5 into 13 minus 1, that is also square. So the question is, now you take any one more number D, right? All of them cannot be square. So like 2D minus 1, 5D minus 1, 13D minus 1. All of them cannot be square. So one can always find two numbers A and B, and one of the numbers should be what D, because if I choose any of these two numbers, right, then each of them gives me square. So I can pick up one from this and one D, and the product minus 1 is not a square. Okay, again? Yeah. So to prove that 2d minus 1, 5d minus 1, 30d minus 1, all can't be squares. All can't be squares. Okay. Once again, show that one can find distinct AB. I can find two numbers out of this, two different numbers. So that product minus 1 is not a square. Okay. And method is typical by contradiction. So you assume, suppose possible, all of them are squares, and you get something wrong. Okay. Suppose possible, it's called as method of contradiction. जो भी प्रूव करने का पहले उसको ना बोलो, as simple as that. So suppose possible, all of them are squares. Yeah. So we go ahead. Suppose possible, 2d minus 1 is some square, 5d minus 1 also is square, and 13d minus 1 is also square. Suppose possible, all of them are square, you will get something wrong, that is contradiction, and therefore all can be square. So at least I can find one number along with d, so that product minus 1 is not a square. Yes, once again, parity comes into picture. What surely we can say about even odd of x, y, z? Like 2d minus 1. So shall I say x square is odd? Okay. And if x square is odd, x also must be odd. What else we can say? I can say x should be odd. What about y and z? Can we say something? If I know the parity of d, then I know what are y and z. Okay? So I should know something about d. Now if x is odd, shall I say x is of the form? X is 2k plus 1. Right? Odd numbers are 2k plus 1, right? Even numbers are 2k. Okay? So x square is 4k square plus 4k plus 1. 2k plus 1 whole square. Okay? Which means from these two terms I can take 4 common. Right? So 4 times something. What is that? K square plus k. Shall I call this as 6q, 4q plus 1? So if x square is odd, x is 2k plus 1 time. So that means x square is 4q plus 1 time. Okay, I put it there. So it implies 2d minus 1 is 4q plus 1. Now you tell me what should be d, even or odd? You can simplify that equation. Get d equal to something and tell me whether d should be odd, even, whatever. ऐसा इवन और मत बोलो, d क्या आता है बोलो, what is d? d is 2q plus 1. All of you agree? Are you getting that? 2d minus 1 is 4q plus 1. So 2d is 4q plus 2. So d is 4q plus 2 by 2. That is 2q plus 1. Now what is 2q plus 1? Even or odd? Even plus 1, right? So D must be odd. Now can I say something about Y and Z? So I know D is odd, Y is odd, odd into odd is odd, odd minus 1 is even, so Y square is even. Similarly, Z square is even, right? So shall I say D is odd implies Y square, Z square are even. But if Y square, Z square are even, that implies Y and Z are even. Okay? Yeah. Now it's subtract. So what is Z square minus Y square? Z square minus Y square. This minus this, 80. Right? Z square minus Y square is 80. So one cancels. Right? What is this number? It is even, right? And with Z square minus Y square, Z plus Y into Z minus Y. That is 8. So everything is fine. This side is even. This side is even. I mean, both are even. And D is odd. D is odd. Okay. Now you see difference between these two. Difference of Z plus Y and Z minus Y is. So you tell me what is the difference?
2y.
2y, and already I know y is even. So that means this is multiple of 4, which is multiple of 4, right? Because 2 divides this, so 2 times that, so 4 divides it. Okay, agree? So 2y, y is even, so 2y is multiple of 4.
Yes.
So good? Yeah. You want to get some contradiction, keep that in mind. So far we haven't found anything wrong. Everything is fine. Yeah. Now look at some pattern of even numbers. Say 2, 4, 6, 8, 10, 12, 14, 16, and so on. Now look at those numbers which are with a difference of 4. And difference of these two is multiple of 4. So numbers which are with a difference of multiple of 4, 2 and 6, difference is 4, right? Then 2 and 10, difference is 8. 2 and 14, difference is 12. So these are all multiples of 4, right? So which numbers have difference multiple of 4?
Sir, sir, I different method.
This. Okay. So what are these? 2, 6, 10, 14, 18, and so on. They all have difference which is multiple of 4, or 4, 8, 12, 16, and so on. They also have difference which is multiple of 4 into something, right? So see that all these numbers are 4k type, 4k type, and all these numbers are 4k plus 2 type, right? What is 6? 4 into 1 plus 2. What is 10? 4 into 2 plus 2. What is 14? 4 into 3 plus 2. Right? And so on. So these are all 4k plus 2 types. These are all 4k type, multiples of 4. Right? So can I say that difference of these two is multiple of 4, which means either both must be both z plus y, z minus y must be 4k plus 2 type or 4k type. Both 4k type. Okay. Now if both are 4k plus 2 type, this product is not multiple of 8, right? Because only 2 divides this, 4 does not divide any number. So maximum 4 will divide the product. So check the product, 2 into 6, 12, which is multiple of 4, not 8. 6 into 10, 60, which is multiple of 4, not 8. And 10 into 14, 140, multiple of 4, not 8, and so on. So what we have is, this product will be, so if both are 4k plus 2 type, both are 4k plus 2 type, implies LHS is 4 into odd number, right? 4 into odd number, and RHS is 8 into odd number. Right? Do I get some contradiction? 4 times odd, 4 times odd equal to 8 times odd. So 4 1 are 4, 4 to the 2, so 4 to the 8. So odd equal to 2 times odd, right? That is wrong. Okay, agree? Odd is 2 times odd, that is wrong, right? And if both are 4k type, both are 4k type, so I get, in that case, 4 divides this, 4 divides this. So shall I say this was 16 times some number, and this side I have 8 times some number, odd number. So again, 8 1 are 8, 8 2 are 16, and 2 times odd is odd. So I get odd equal to even. Right? So in both cases I get odd equal to even. Either LHS odd, RHS even, or RHS odd, LHS even. Where should I write now? Okay. So in both cases, we get odd number equal to even number. Odd equal to even. Okay? Which is contradiction. And anyways, why do we get contradiction? Because our assumption was wrong. So, right? So what did we assume? That 2d minus 1, 5d minus 1, 13d minus 1. All three of them are squares. That is wrong. So at least one of them is non-square. So one of yeah. Again, there is some theory related to this problem. Let me tell the problem. You can complete the write-up. Okay, so though difficult, we have solved one IMO question, right? It's comparatively recent IMO question. 1986. So you are saying,
Sir, can you write the equation 2d minus 1 is equal to x squared, 5d minus 1 is equal to x squared?
yeah,
Can you write it?
yeah. Can I have this side? All of you? Yeah, 2d minus 1 is x square.
5d minus 1 is equal to y squared. 13d minus 1 is equal to x squared. So sir, let's suppose d is equal to 10k plus 1. Sir, then the unit digit of z square becomes 2, which is not possible. So d equal to 10k plus 1.
But why d should be 10k plus 1? There are other forms, right?
Yes sir, I will.
Okay, I got it. D is 10k plus 1.
Sir, then the unit digit of z square becomes 2. not possible.
Yeah, good.
Sir, then the second case is p equal to 10k plus 2.
Just a minute, just a minute. So all of you agree that square does not end with 2, right? Square ends with what? Square ends with 1, 0, or in fact 0, 0, 4, 9, 5, in fact 2, 5, 6. Yeah. So z square ends with 2, which is contradiction. Good.
Sir, second case p equal to 10k plus 2. The unit digit of x square is equal to 3, which is not possible.
If d
Equal to 10k plus 2, unit digit of x square becomes 3, which is not possible.
what in fact we have already proved d is odd. So you may not consider 10k plus 2 and so on. And directly having 10k plus 3.
Yes, sir, in 10k plus 3, unit digit of z square becomes 8.
For which one?
Z square.
This one, okay. Then 13b minus 1. 130k plus this is like 8. Okay, yeah.
This is not
Again,
possible. And
z square ends with 8. This is contradiction. Yeah, this is good. D is nk plus 5. We should consider only odd cases.
sir, I cannot put for 10k plus 5, but I have put for 7 and 9. 10k plus 5.
Why? Okay, so this we have to settle. Okay, fine.
And sir, if d equal to 10k plus 7, unit digit of x square becomes 3.
Okay, all of you, so this is exercise for all of us. Try to settle this case. Yeah. So if d is 10k plus 7,
Unit digit of x square becomes 3.
20k plus 14 minus 1 3. Yeah. So this is, so implies x square ends with 3. This contradiction.
And sir, if d equal to 10k plus 9, unit digit of x square ends with 7.
Again x square.
X
B minus 1 is
10k. D equal to 10k plus 9.
yeah. So it ends with 7. So except this case, d is 10k plus 5, we have settled every other case. This we are complete. This again a contradiction. Yeah, good, very good. I think this can be settled. You can try that later. Yeah, it's a nice group. Of course, not complete, but it's very nice. Nice.
Sir, how much marks this answer will get?
Depends in fact, you haven't proved that perfectly. But still, there are marks for it. And I mean, good number of marks. So for example, if this is for say, 14 marks, you get more than that. Olympiad is not more about marks, it's more about participants. Yeah, I was saying something. So something related to this problem. There is old problem called as tripartite That fertile pupils, which is exactly opposite. So can you find five integers such that AB plus 1 is 12 for every parent. Okay. And in fact, it's proved now by some Indian mathematicians like Ramurthy, some Dixit Ramurthy, they have proved it that phi is not possible. In fact, maximum 4 is possible if you are talking of integers, and Verma gave 4 such numbers. So like 1, 3, 8, and you see 1 into 3 plus 1, which is a perfect square. 1 into 8 plus 1, which is a perfect square. 3 into 8 plus 1, which is a square. And in fact, fourth number is 120. Check for this set, every AB plus 1 is a square. But phi integers is not possible. In fact, if you replace integers by fractions, rationals, then phi is possible. Let me give one such example. You have order. Sorry, this is for 4, and in fact, Euler extended this set with rational for the fifth number. So if you take these 5 numbers, of course, one of them is not integer rational. So Euler extended this Verma set to 5 numbers, where one of them is rational. Then you take again any product plus 1, and you can show that it's a perfect square. Some rational number. So with just one more problem, then we'll stop. Let's use PHP in number 8. That's one more technique from number 8. Two, there is this, and integer made up of only one, which is divisible by 7. In fact, there is nothing special about 7. In that problem set, I have given 20, 23. Okay? Yes. And more generally, it can be divisible by any n, where GCD of n and 10 is 1. The GCD of n and 10 is 1. So we'll do it for 7, and same you can do it for 20, 23 or any n, which is co-prime with 10. Okay? That's last we'll do. We'll stop there. Okay, so idea is following. And show it for 7, and on civil and secondary for 2023. Okay, so anyways, consider one amount number made up of only ones. They are called as definites. Definites, and they have some certain nice properties. It's denoted by R and it contains n ones. So if R2 is 11, R3 is 111, and so on. Then consider following numbers: 1, 11, 111, 4 ones, 5 ones, 6 ones, 7 ones. And I take one more than this because I want to use PHP. Right? 5, 6, 7, 8. Yeah, so idea is I divide each number. So if I want to prove it for 7, I take 8 numbers, 1, 1, 1, 1, 1, 1, and so on. Divide each by 7 to get remainders. Say for first number I call it remainder 1, second number I call remainder 2, third number I call remainder 3, fourth I call R4, fifth I call R5, sixth I call R6, R7 and R8. Now if some of them is 0, one of them is 0, then we are done. Right? So if some Ri is 0, now what's meaning of remainder is 0? When I divide certain number by certain number, I get some portion and remainder 0. Then I should divide say remainder is 0. Then I should divide say yeah. So if some remainder is 0, then 7 divides that number. Right? I. Okay. But I don't know what are reminders. So otherwise, I'll ask you this way. Otherwise, we have 8 reminders, right? And what are the choices? Right? When I divide by 7, what are the possible reminders?
0, 1, 2, 3, 4, 5.
0, 1, 2, 3, 4, up to 6. There are 7 choices. There are 7 choices, namely 0, 1, 2, 3, 4, 5, 6. Okay? You have done PhD? Single principle? Okay, so in this case, my 8 reminders are pigeons. And those values 0 to 6 are my pigeon boxes. I have to put 8 pigeons into those 7 boxes. So one of the box will contain 2 pigeons. Right? So shall I say by PHP? By PHP, 2 of the reminders must be same. They fall in same box, right? Must be same. Okay, yeah. But if 2 numbers give same remainder, if A is equal to, for example, n times some quotient plus remainder R, B is n times some quotient plus same remainder R. What can I say? If I subtract A minus B, R cancels, n times Q1 minus Q2, right? So if numbers give same remainder, difference is divisible by n. Okay? Yeah. So if two remainders are same, implies corresponding numbers have difference divisible by 7. Yes. So for example, quickly let's find remainder for each of them. When I divide 1 by 7, remainder is 1. When I divide 1 by 7, remainder is 1. For 11, 4. For 111, 6. For 1111, 5. And for this is 2. In fact, one of the remainders will be 0 because 7 divides that. Yeah, this is 0. So, for example, say this number and this number have same remainder, and the difference will be divisible by 7. Or this number and this number have same remainder, difference will be divisible by 7. So 7 divides this minus this, right? 1. So what I get? This minus 11, I get last to 0, right? And 6 ones. Then okay. 7 divides 1116 times 2 zeros. Or it means 7 divides 1111 6 times into 100. But 7 does not divide 100. In fact, GCD is 1. GCD is 1, no common factor. Implies that 7 divides totally this. 7 divides 1111 6 times. And you can actually check this is number containing only ones and divisible by 6.
Can I show you?
You write down everything is a bit long. Right? We'll see. I think we'll see.
But I also have a few using
Not yet. Obviously. Yes. Okay, so this was last problem I wanted to say. Time already. We'll stop. Once once again, another important technique as far as geometry is concerned is congruence and theorem of congruence, which I haven't done here. Maybe later on, we give a chance to meet and talk about congruence and see here. This I haven't done. Except that I've said many things, interesting things from number theory, as well as different techniques from number theory. And moreover, what's more important is we have solved every type of problem. Union RMO, right? PRMO, IOQM, RMO, INMO, and IMO. So we have done every type of problem in these problems. Fine. Let's stop here. Thank you.
I would like to thank sir for teaching the concepts of number theory, and I also would like to. Hello. I would like to thank sir for teaching the concepts of number theory, and I would also like to thank him for question-oriented teaching. Thank you.
Then be seated for 5 minutes, sir. Be seated for 5 minutes. Good evening, students. Please be seated for 5 more minutes, and you will be given a form. Please fill it sincerely so that it will be useful for us. It's clear. We are going to give one feedback form. Please write it. Okay?
Okay, all of you, all the best.
Children, please don't discuss with others. It is your own experience. Okay? Whatever you felt that you can write. Nobody is going to question you. Understood? Then some children have come late and you can write only about those sessions which you have attended. You can put a dash, there is no problem.
Number there, 54321.
Children, the instructions are given there on top. You see, please mark chosen answer with 5, 4, 3, 2, 1. If you agree with the statement strongly, you can put 5. For example, the course aims were made clear at the start. If you agree with this really, you can write 5 over there. And just you can agree means you can write 4. If you are neutral, I neither agree nor disagree because I did not pay any attention. So you can write 3. And disagree. Whatever is given is not meant means you can write 2 and strongly disagree. Nothing has been done. If you feel you can write 1. So it's your will and wish. Please don't discuss and we will not get the real feedback. I need someone discussing and writing. Still, some of you are discussing and writing. We want real feedback, original feedback.